Hello, welcome to an extra example of a homogeneous linear system. So we're going to show that a given matrix will be our fundamental matrix for our differential equation system. That fundamental matrix, psi of t, is our solution matrix. So once again, we are given a solution. We are simply verifying that that works as a solution for our given differential equation, all right, or system of differential equations. So over here we have y prime equals that coefficient matrix, which we can call A or we can call P of t times y. So we want to form the general solution. Actually, let me not skip to that. Let's go ahead and prove that that is in fact a fundamental matrix. Now, one thing we could do is take each individual column, find its derivative, and verify this using substitution. I won't go through and do that again. We did that together in class when we did this the first time. What I'm going to do is simply verify using the Wronskian. So we are going to find the determinant of psi, or you could also say that this is the Wronskian. I guess that kind of looks like omega. Let me do W of t, Wronskian that way. Either way, you write that. That would look like 1 times 0 minus 0. So that goes away. Minus e to the t times our 2 by 2 determinant here, 0 plus 2e to the 2t. And then plus e to the 2t times that 2 by 2 determinant, which looks like that's going to be 0 minus 0. So that also goes away. So our Wronskian is a negative 2e to the 3t, which is not equal to 0. So that verifies that we do, in fact, have a fundamental set. All right, does form a fundamental set. So that means we can now form the general solution. So again, this is working in the back half of the problem. Once you have a solution, form the general solution, and then in the case where we have an initial value problem, we would go ahead and solve it. So the general solution we want to write as, let me move it over here actually, y of t. All right, now that's going to be equal to our solution that we got here for psi. All right, so all that written out, and then that is going to be multiplied by C. So C1, C2, C3. All right, because anytime we're forming our general solution, y is just going to be equal to our psi matrix times that C matrix, the vector value function for C. So you can leave it like this. I'm going to do the matrix multiplication and say that that in fact would look like this. All right. So again, multiplied out is another variation on writing it. Sometimes it does benefit us a little bit, and specifically with initial value problems, once we find those values for C, we do plug them in and write it as that. We do prefer that second version of writing out the solution. Okay, so given the initial value problem, and I'll include that here in just a second, we're going to find C. Now, remember that in order to solve an initial value problem, that essentially we are taking this general form or this form of our general solution that we have here, and we're solving for C, which means that we are taking the inverse of our psi matrix, evaluated at our initial value. We will be using 0 as our t there. Okay, and then that's going to get multiplied by y of 0, and then that's going to give us C. So that's what we're going to do. So here's our initial value for this problem. If we evaluate y of 0, we are getting this solution matrix here, 0 to -2, or our constant matrix, I guess. Okay. Now, in order to find the easiest way to do our inverse here is to first evaluate our psi matrix at 0. So let me get rid of my inverse notation real quick, and let's just go and evaluate that at 0 first, just to make our lives a little bit easier to find the inverse. Now, again, once you have constants in here, it may be a little easier to use a Cramer's rule. Again, you can use your calculator to find the inverse. There is an inverse option in that matrix menu. So that is not against the rules here with what we're doing. Looks like we are going to have this as our matrix. And then, yeah, to find the inverse. And so again, you've got a variety of methods. I'm not going to include that in this video. If you do have questions about that, I know because there are so many methods, it is tricky. And so if you need any help with that, let me know. What I got here for the inverse is this matrix. So if you want to pause the video and do any of those methods that we've discussed in class for finding the inverse and make sure you get the same thing, you can do that right now. Now, once you have the inverse evaluated at that initial value, and we have our initial condition, that is our y of 0, this property is saying, because we solved this equation here for C, that we have to take and multiply those. And obviously, we write it in that specific order because we have matrices. The order matters. And so we are going to take our 3 by 3 and multiply it by our 3 by 1. And then that should give us our values for C1, C2, and C3. So I'm just going to write out here what I'm multiplying it by 0 to -2. And I am getting for this, I got 1 for C1, -2 for C2, and I got 1 for C3 by doing that matrix multiplication. So this is what we are saying is equal to those values of C. Once we find that, we do want to plug everything back in. And that's why I say using this second version of writing out that solution, which in our case will be our particular solution, is probably the more popular. Sorry if there's going to be some background noise at the end of this video. But y of t then would look like this. 1 minus 2 e to the t plus e to the 2t. And then we get 2e to the 2t and -1 minus e to the 2t. That will be our general solution. Now keep in mind, these are 3 variations or 3 equations that form our solution. So one solution, y1, would be that 1 minus 2e to the t plus e to the 2t. And we could write the same for y2 and y3. So remember, if we're solving a system of differential equations, we actually get 3 equations that form our general solution, and they are all written as elements inside of this matrix here. All right, let me know if you have any questions. I hope you have a great day.